Hello everyone, it's July 29th. Alright, let's get started. Word subsets. You are given two string arrays, words 1 and words 2. A string B is a subset of string A if every letter in B occurs in A, including multiplicity. For example, word is a subset of warrior, but is not a subset of the world. A string A from word 1 is universal if for every string B in word 2, B is a subset of A. Return an array of all the universal strings in words 1 and return the answer in any order. So, Facebook, Google. What do you mean by multiplicity? If for every letter B occurs in A, including so like has to have two R's. I mean, we can turn word 1 into a counter and turn this into a counter as well, and then just see if this is included in that. How do we do that? I mean, counter we can minus, right? All the strings of words 1 are unique. So if you think about it, for each words 1, you have to do words 2, all of them. All of them. Which if you do that, that's going to be O1 squared, which is not going to work. But what you want to find is a words 1 as a universal. So all I need to do is go through words 2, create a counter, universal counter, and then just to check. So we just need to go O(n) to create a universal counter, and then we compare this counter to that. And how do we compare? Well, we can minus two counters, right? If we minus two counter, what's going to happen? I actually have no clue. What is going to happen if we minus two counter? Let's say A equal, hold on, from collections, import counter. Okay, A equals counter, let's do Amazon. B is a counter, let's do LE. Okay, so A is this, B is this. How about A minus B? Well, A minus B, it's not going to give you any negatives. It's just going to be that these are no longer existing. Why do you do that? Once we get a universal counter on B, we can just iterate through everything. So at most it's going to be 26, right? At most it's 26, and then everything we can just check. That actually might be a better idea, honestly. I think it's going to be a better idea. And we can even do a quicker check because it has to be universal, right? So if the length of the universal on words 2 is larger than the length on 1, that means it must be something that doesn't match. So we can just ignore those. So that will be a faster check on sum. Okay, now how do we create a universal words 2 counter? It just says on this, right? So what we can do is just counter it, right? We can just go through every single one. Well, actually, we need to counter one, and then we create a universal counter, and then for each one is going to be a counter, and then I'm going to combine these two. And how do we combine these two? What we're going to do is just record the maximum, right? The maximum count of a letter. If we have a letter, we have like occurs 2 times on here, occurs 1 time on here, and overall it's going to occur 1 time. So what we can do is just go through every letter Now I can go through the counter, go through every key in the counter, and then for the universal counter, we can just record the maximum one, and then we can create a universal counter for word 2. And after doing that, we compare to word 1. I think this shall work. Still have no Ghana for the other one. Okay. So what we're saying is we have counter uni counter. Okay, we can just do a counter, and we say for word in words 2, right? And we say for letter count in counter word dot items, and uni counter letter equals maximum uni count letter and C. So once we're just done, we just say for word in words 1, right? And then we just say for letter C in uni counter items, if len uni counter is smaller or equal to len, we can do a counter. Counter equals to counter word. So smaller than counter. And then we do this. If counter letter is smaller than unicounter letter, well, which is basically just C, right? If it's this, then we're gonna break. Else, say rest.append word. We need to create a res, it's here. Okay. See if this one works. Okay. Okay, passed. I'll do some tests. Edge case. I consider this as edge case. Could be. All right, try this. Okay. All right, let's just take a look at the methods used last time. Oh, you actually go to solution 2. 916. What do we call? O. I call ON plus M, where N and M are length of words 1 and words 2. I mean, technically speaking, we have to go through every single letter, but because we counter it at first, so it's going to be 26 at most. So it's Yeah, I think it's not going to be too big an issue. We're just counting it as that. Oh, there's a counter magic. Oh, we'll do the minus in reverse. I was close. I knew it. There gotta be some. Oh, hold on. We have to import it first. So A minus B, nothing happened, but B minus A. Didn't really work, right? Because this does not exist. Yeah, so see if I do counter AM, and I will do C minus A. Ah, so it can completely. So from C, I remove A, I remove these. Ah, that makes sense. Ah, nice. Very nice. It is a global counter, and I use all. Operations. See, this is something I don't remember. Too long time ago. Too long time ago. Yeah, now I know it's a dictionary, it's all fine. Addition is easy to understand. Subtraction. Common elements are subtracted from each other, and then keep only the positive count, okay? Intersection. Oh, and. Keep the minimum. Oh, that's true. An intersection will always keep the minimum. Oh, as a union will keep the maximum. Damn. Interesting. Interesting piece of trivia. Could be useful, right? Yeah, let's put it here. Repeat what I did in March last year. There are counter magic in Python. Okay, so we can say uni counter. Yeah, we still do uni counter equals this. Right, equals counter. I say for word in words 2 uni counter union counter word, and I'm gonna return word for word in words 1. If not, which means we can remove all of them, unicounter minus counter word. Yep. What a brilliant solution. Counter magic. Very interesting. Ha! It's always slower. Reduce to single would be, yeah. Okay, so this one is done, but that's a good article. Alright, let's try this one. Maximum total importance of a road. You're given an integer n, denoting the number of cities in a country. Cities are numbered from 0 to n minus 1. You're also given a 2D integer array of roads, where rows I is AIBI denotes that there exists a bidirectional road connecting cities AI to BI. You need to assign each city with an integer value from 1 to n, where each value can only be used once. The importance of a road is then defined as the sum of the values of the two cities it connects. Return the maximum total importance of all roads possible after assigning the values optimally. So these are the roads, right? And then we need to assign values, and we need to find the maximum total, right? The maximum total. So like say this one will be a 6, that's a 9, that's an 8, that's a 7, that's a 6. Interesting. There are no duplicate rows. Huh. We want to assign the points such that. So isn't that equivalent to saying if we want to traverse all the roads, then we want the value to be the maximum? Hold on, let me think. If we traverse the roads, and when we traverse, each is counted only once, then the results will always be the same because each node is visited once. But now, if we do all the traversal, like we visit every single one, then some will be visited more often than the others, right? So we shall put the maximum value on the nodes that visit the most often. So can we do it greedily? We produce a adjacency list from this, right? And then for the nodes with the most neighbors, like in this case, this one has the most neighbor, so we're going to assign the maximum value to it. Assign the maximum value to it, and the rest will be the same. I think that is the case. I think this one is nothing too special about this one. When I see that, the first thing in my head is Dijkstra, and I was thinking, okay, can you call Dijkstra? And oh shoot. And I was like, I don't think I can call Dijkstra. Dijkstra, oh my god, can you call Dijkstra? So we start from a node, right? And then we push all its neighbors to a priority queue with their score, either maximum or either minimum, doesn't matter. And then the first one pop out, right? And then once it pops out, because that's the current path that we take, and now we find all its neighbors, and we update, right? We update its score, so we need a dictionary to keep track of the current score. So we look for the previous score and add the current, and then we just push it back into the queue, right? And every time it pop out, if it's something that's been recorded before, and if the score is not optimal, we just skip. Yeah, I think that is Dijkstra. I might be able to code it, but I think if I need to go through interview it again, I most likely will have to redo it, the Dijkstra thing. Like just go through the whole thing again. All right, anyway, so what we need to do is to use they say 0 to n, right? 0 to n minus 1. So I can just say I just need to count. I don't even need to record, so I just need to count. So we just say counts equals 0 times n, right? And then we say for A and B, A, B in rows. We say counts A plus equal 1 and counts B plus equal 1, right? And after we do all that, we are going to sort it, right? And then we sorted it, and hold on, let me check. This is 1, 2, 3, 4. 4 times 5, 20, right? 20 plus 12, 32. 32 plus 6, 38, 40, 40, 41. Let's do that again. 1, 2, 3, 4. 4 times 5 is 20. Right? 1, 2, 3. 3 times 4 is 12. 20 plus 12, 32. And we have here is 32. 32 plus 6, 38. 38 plus 4, 42. 43, yes. So we just need to sort this counts and do that, right? So we can say for C in sorted counts, okay? And well, actually I should say for oh, it's perfect, because sorted is a small at first. What are you doing, man? Enumerate. All right. So we say enumerate this, and then we can have an I and C, and C times basically I plus 1. Right, and then we return the sum of this thing. That shall do it. 43. This shall be 20. Oh, shoot. Oh, shoot. Press the wrong button. Okay. So in edge case, n has to be equal to 2. Okay. Rows has to be 1. Oh, I said 2. Let's try this. Oh. All right. So this is deterministic. So assign the largest, what they call a score, importance to the city with the most number of neighbors. Isn't that called a degree? Is that a degree of a node? Is that called a degree of a node? Therefore, this problem is deterministic. I mean, they're all deterministic. So this problem has no branches, does not branch out, does not need any search strategy, and we can do it in ON. Yes, N is the ON. Okay, that shall be it. I don't think there's any anything. Note degree, yeah, so by degrees. Exactly. Okay, so as done by this, so I actually can move on to the next one. Now this one is tough. I think the passing rate is only like 17%. And lordy, it's also long too. Oh gosh. Great. Okay, so I'm not gonna do this. I'll have to just deal with the other one first. There's no point if I haven't dealt with this one. I mean, this is currently it's not correct. See that? It's not correct. So I have to, yeah, I'll handle this. Maybe handle this tomorrow, and then we roll into this one. Okay, that'll be it. See you guys tomorrow. Adios.